Welcome back. We are going to continue our discussion of thermodynamics, and we're going to sort of take a little tangent. We have learned about the first law, which talks about how energy is conserved, and gave us an understanding of heat and work, which are two ways to move energy. And really to understand equilibrium, which is what I promised we were on a road to, you have to understand the second law and then think about how chemists use that in reference to deciding if a process is spontaneous or if it's at equilibrium. So right now we're just going to take a little tangent and really go over what we did in Chem 107, thinking about how you can deal with thermodynamic functions. So this first section, share the screen. So we're on topic 2E, and we're going to first just talk about physical change. So we've learned about the function enthalpy, which a change in enthalpy, is equivalent to the heat transfer in or out of a system if the process is carried out at constant pressure. So we're going to use that function because that's a common way to set up an experiment. And the important thing, the key idea to come out of this is that enthalpy changes for individual steps may be added together to obtain the enthalpy change for the overall process. And you remember that as Hess's law. It's also just a result of enthalpy being a state function. If enthalpy is a state function, doesn't matter how you go from reactants to products. If you're carrying out a reaction, you could do a 5-step reaction, a 1-step reaction, and Hess's law would say that all that matters is where you started and where you ended up. So some of the things we have to remember about thermodynamic functions is, number one, their values depend on the conditions. So what the pressure is, what the temperature is, what the quantity is. And so we're going to define a standard state so that when we look up thermodynamic functions, we'll know what we're dealing with. So the standard state of a substance is the pure substance at exactly 1 bar. In your Gen Chem text, the old convention was still being used, that standard state is 1 atmosphere. So all those tables would be slightly different numerical values, but 1 bar is the accepted new standard for a standard state. Also in Gen Chem, you may remember thinking that the standard state included the temperature, and that's not really correct. So the only thing that we see here in our standard state, it's the standard state of a substance, is the pure substance at exactly 1 bar. So the temperature can change. You can report it at different values. Our tables will report the values at 298. Yeah, 298. And so we'll know what the temperature is, but sometimes we may have to think about a different temperature, and it can still be the standard state. So when we talk about physical change, we're talking about phases. So a phase is a specific state of matter that's uniform throughout in composition and physical state. So we can have liquids and solids, and a solid can have more than 1 phase because it can have more than 1 structure. So something like sulfur stacks differently, and you get 2 different phases. So you have to make that clear because the enthalpies are going to be different. The conversion of 1 phase of a substance to another is called a phase transition. So you know a lot about phase transitions. Liquids can become gases, solids can become gases, things can melt. So we'll talk about all of those. The table here just gives the delta H at the temperature at which it is in equilibrium. So that's often the case. So standard enthalpies, but the temperature is not 298 because we're reporting these at the temperature at which the process takes place in equilibrium. So just some of the nomenclature. Standard enthalpy of vaporization is just the heat at constant pressure that it would take to vaporize 1 mole of something. So to make it go from liquid to vapor. And we usually write thermochemical equations to represent what we're talking about. So we're talking about vaporizing water. We're taking liquid water to gaseous water. And if it's a thermochemical equation, right next to it, you'll put the delta H for that process. Notice it doesn't have any quantity, but it would be per mole because each of these is a mole. So let's look at self-test 2E.1 on page 64. Says in a similar experiment to the one in front of it, it was found that 1.36 grams of boiling benzene is vaporized when you pass a current of 0.835 amps from a 12-volt source for 53.5 seconds. What's the enthalpy of vaporization of benzene at its normal boiling point? So if it's boiling, okay, I'm gonna take 1 second. Hello? Oh, it's fine, what's up? Okay, I'm here. He's out riding, but he should be home soon. Okay. Bye-bye. Sorry about that. So back to this problem. And the standard boiling point is defined as the boiling point when the pressure is 1 bar, the normal boiling point when it's 1 atmosphere. They're pretty close to each other, so, but just keep those in mind as definitions if you're given one or the other. So it tells us the current in amps is coulombs per second. If you multiply coulombs times volts, you get joules. And if then we multiply by how long we pass that current through, we get the total quantity in joules of heat that was supplied to the benzene to boil it all, or to vaporize it all. So we have 1.36 grams of benzene, molar mass is 78.11 grams, and so we have 0.0174 moles of benzene. So took 536 joules, and that was when we vaporized 0.0174 moles. So if you take the ratio, essentially you're deciding how much it would take for a total mole, and I get 30.8 kilojoules per mole is the delta H of vaporization of benzene. And I just wrote Wolfram Alpha there because you might find Wolfram Alpha is a useful tool to do some of your math. This is just pointing out that the enthalpy of vaporization is really a measure of how strong the intermolecular forces are. So water has a super high enthalpy of vaporization because of those strong hydrogen bonds. Something else like methane, it would have a much lower one. I think it says here water is 40.7 kilojoules per mole and methane is 8.2 kilojoules per mole. So when you're vaporizing methane, you're just breaking those weak London dispersion forces. So it doesn't take a lot of energy. Another phase transition is fusion, which is also melting. And so you can have standard enthalpies of fusion. Excuse me. And then the reverse of fusion is, the reverse of vaporization is condensation, and the reverse of fusion is freezing. So because of Hess's law and the fact that enthalpy is a state function, if one direction vaporization for water is 40.7 kilojoules per mole have to be supplied, then if you were to condense 1 mole of water vapor, it would just have the reverse sign, so it would be negative 40.7. So that's really just pointing out the fact that enthalpy is a state function. So one direction takes energy, the other direction gives up exactly the same amount. Sublimation is the process of going straight from solid to a gas, and vapor deposition is the opposite, going straight from gas to gas to a solid. So we have standard enthalpies of sublimation, and once again, because of Hess's law, if you knew how much it took to take the solid to a liquid, and then second, the liquid to a gas, you'd add those two together because those two steps are the same as sublimation. So once again, that's just Hess's law. So the enthalpy change of an overall process is the sum of the enthalpy change for the steps into which it's divided. So that's all that's saying is enthalpy is a state function. So this self-test says deduce the standard enthalpy of vaporization of liquid carbon dioxide at 298 from the standard enthalpy of sublimation and the standard enthalpy of fusion at that temperature. So that's very easy. They give us sublimation, they give us fusion, and we're just solving for X, which is the vaporization. So the sum of melting and then vaporizing is the same as sublimation. And so I get 16.90 kilojoules per mole. We talked about this also in general chemistry, and there's nothing really new here. The standard enthalpy of ionization is the heat it would take to ionize a mole of a substance, so take off 1 electron. You can have enthalpies of ionization for the first electron, for the second electron, and here's just a table of a bunch of their values. So these are good problems to think about Hess's law. So the reverse of ionization is electron gain, and an standard electron gain enthalpy would just be take something, add an electron, and that's very similar to an electron affinity. So let's, for the last thing, just do this problem right here. The enthalpy of sublimation of aluminum is given. Use the information in the ionization enthalpies in the table to calculate the energy that needs to be supplied as heat at constant pressure to convert 1 gram of solid aluminum metal to gaseous aluminum ions. So we want this right here. We want to determine the delta H for this step. And so we have other enthalpies for other steps that would get us to the same place, would take us from solid aluminum to gaseous ions plus 3 electrons. The first is sublimation. So take the aluminum solid and make it into aluminum gas. Then the next would be take 1 electron off, take 2 electrons off, take the 3rd electron off. So this would be the first ionization enthalpy, the second, the third. So we're going to add together the sublimation enthalpy, the first ionization energy. Notice they get bigger and bigger. You take more and more electrons off, it gets harder and harder to do. And so sublimation, first ionization, second ionization, and third ionization. So each of those comes out of the table. The sublimation came out of the problem, and this would be per mole, all those added in red, but we need to figure out when we only have 1 gram of aluminum. So I'm going to multiply it by 3.71 times 10 to the minus 2 moles, which I just did up above. And so I get 203 kilojoules. It would take to take solid aluminum and make it into gaseous cations and 3 electrons. So that is all for topic 2E. So we have one more topic left, and then we'll move on to the second law.